Hi, everyone. So in this unit, which is essentially the finite unit in the proof of the R transform theorem, we are going to give an explicit formula for the additive free finite convolution in terms of the coefficients of the actual polynomial. So no expectations over R, just like an explicit formula in terms of coefficients, as explicit as you would expect. And we are also going to give some other alternative and equivalent definitions. Interestingly, one of them is with respect to the roots of the two polynomials rather than the coefficients. I actually hinted it in one of the live lectures that we had, I think the previous lecture. And we're also going to see the explicit formula is great because it's explicit, but it's actually not so easy to work with. So we're also going to consider maybe a slightly less explicit formula, but it's kind of easier to work with and analyze stuff with. Okay, so let's just start. Okay, so this is our unit. We are again following the finite free convolution of polynomials paper by MSS. So the idea would be actually not to give an explicit another or a more explicit formula for what we denoted defined as this thing, as the additive free convolution. Instead, we're actually going to redefine this symbol, and we are going to do it in a more general setting. Namely, we are going to define it for arbitrary real-rooted polynomials, or we're considering root polynomials, but arbitrary polynomials, complex value polynomials. And the main theorem will be, I mean, that's going to be very explicit, and the main theorem is going to be that when we restrict to this new operator applied to characteristic polynomials of matrices, when we get back our original definition. Right, so we're actually going to generalize the definition, and we're going to suggest a new definition and prove that that definition, which is more general because it works for general polynomials, when restricted to characteristic polynomials of matrices, normal matrices, it is equal to this thing, to that thing, which is how we defined initially the additive finite free convolution. Okay. So from here on, we're actually going to consider polynomials more generally, and let's just get right to it. So let's say we are looking at 2-degree at most D polynomials. And usually when you write the polynomials, you write it, sum of ai x to the I. Here it will be more natural and, we'll have to work with less signs and carry them and so forth if we are going to do it kind of in the reversed way. So namely, we are going to given the polynomial p of x, the coefficients are going to be the ai's, but a0 is actually the coefficient of x to the d. Okay, so let's write p of x as the sum I from 0 to d, and the coefficient of x to d minus I is ai, right? So it's reversed, and also includes a sign of -1 to the I. You'll see why it's more natural, but in this setting at least, it's kind of annoying to work with initially, but it's more natural in this setting. So let's say you are given two polynomials p and q in that form. Degree at most D polynomials, it's fine that A0 is 0. Okay, you don't have to have exactly degree D. And the coefficients corresponding to Q are denoted by these BIs. So I assume, quite nothing about them. They are complex univariate polynomials. They don't have to be real rooted. They don't have to be, they can be complex like all the way, right? And we define explicitly the diff-symmetric additive convolution of these two polynomials. So we use the same notation, right? So it requires a theorem. Again, that will be the theorem that will prove that it's justified. So this notation, when restricted to characteristic polynomials of matrices, gives the same thing. But let's forget about that for now, and let's define this operator on two polynomials as this thing. Right? I mean, you ask for explicit, that's explicit. It's kind of long, but it's explicit. So what's going on here? So again, we are really asking what's the corresponding, CI, the coefficient corresponding to this new polynomial, right? So like here, we wrote it x to the d minus I minus 1 to the I times something. So here also, we write it as x to the d minus k minus 1 to the k and times something. And that something, which we'll usually denote by c, is the corresponding to coefficient of this resulted polynomial. And what is it? So it's exactly this thing. It has this convolution-like sum. You go over all I and j. You take AI times bj, all I plus j equals k, AI bj or AI bk minus I. But you have this coefficient. Okay, it's kind of a mysterious coefficient. A priori, it's kind of a weird-looking coefficient. So that's the formula. Okay, so if you believe me that this definition generalizes all definition, then that's the formula that you are looking for. Okay. Okay. So some remarks. So first of all, as I said, the degrees of P and Q are at most D. So when you define this operator, when you apply it, you can only apply it to degree at most D polynomials. They don't have to be degree D polynomials. So in particular, if you have two polynomials of degree at most D, then you can look at the diff additive symmetric additive convolution or the CIF additive symmetric convolution for every C larger than D. And this is not going to be the same in general. Okay. So we are going to see the relation between these two, but it's not the same polynomial. Okay. Secondly, it's quite I think obvious to see from the definition that this is a symmetric definition, right? Because the roles of I and J are similar in the definition, so you can replace A with BJ and so forth. Good. So before proving stuff, let's see some examples. So let's say that P of x is any degree at most D polynomial, but let's take Q of x to be this polynomial, x to the D. Okay, so this is just a reminder of this new slightly weird notation in the beginning. So if Q of x is x to the D, then in looking at this for a second, you'll see that B0 is 1, because B0 is the coefficient of x to the D, because -1 to the 0 is just 1. So B0 is 1, and the rest of the BIs, so B1 up to BD, are 0. Right, so that's what we have here. So what does it mean? It means that for every k, if you are trying to figure out what ck is, then ck was something that looked like this. It was a sum where you summed over all I and j whose sum is k. And then you had this weird coefficient, which let's not get into for the moment. And then you had ai times bj. Now the only j that survives is j equals 0, because only b0 is non-zero, it's 1. So this entire sum actually goes down to just one summand, which corresponds to j equals 0, and therefore I equals k. So when j equals 0, b0 is 1, so you don't see it. It's like times 1. And a of I is ak, because only I equals k survives. And then opening up this thing, it was this expression where I substituted already I and j accordingly, and you get just 1 in this case. So anyhow, what I'm saying is that ck is actually ak. The whole thing, the whole sum goes away, just one summand, and that particular summand is precisely the coefficient, the kind of corresponding, the coefficient of x to the d minus k up to the sign of the original polynomial. So put differently, if you take the additive free convolution, the diff additive free convolution of px with x to the d, you get back px. Okay, and that should not come as a surprise, because if you are, if you believe me that this is actually a generalization of our original definition, then x to the d is essentially the zero, it's like the characteristic polynomial of the zero matrix, all zeros matrix, right? So you can just take A to be any normal matrix whose eigenvalues are those are the roots of P. And B is going to be the zero matrix corresponding to a matrix that has only zeros as its eigenvalues, of course. Then the old definition of the additive free convolution of these two matrices corresponding to these polynomials or characteristic polynomials, well, just B is 0, so everything here is vanished, and you get back P of x, right? The characteristic polynomial of A. Good. So you can do as another example, I think I'll skip it because it's just very technical to follow, but let's just start, at least at the beginning. You can say, okay, let's not consider x to the d, but x minus lambda to the d. Right, x to the d in a sense is kind of the constant zero measure, right? So it shouldn't change anything when you add it to something else. And this is the constant measure on lambda. So you might expect the measure to shift by lambda, and that's exactly what's going to happen. It is a bit instructive to see it in the calculations, but it's expected. So, but maybe let's just start. So if q of x is this polynomial, and again, p is a general polynomial, then let's see what happens. Okay, maybe I'll just start and the boring stuff I'll skip. So x minus lambda to the d, if you open up this thing according to the Newton binomial theorem, you get this expression. Here I kind of chose, you have this choice between who's going to have the d minus j power and who's going to have the j power. Here I chose the x to the d minus j because I want it to kind of be similar to what we have, the way we express polynomials here. And then you have minus lambda to the j. And this means with our notation that bj is actually exactly d choose j. And then you skip this minus and you only take the lambda to the j, because the minus is kind of built in the way that we represent polynomials today. So this is bj. And this means that ck, right, the kth coefficient of the resulted polynomial is, well, you had this formula where you have this, like you go over all I plus j equals k, you have this constant term like that is not dependent on the polynomials, ai bj, but bj is this thing. And now quite a lot get cancelled because, the d factorial from the d choose j get cancelled, and the d minus j factorial get cancelled as well. But you have one j factorial left from this thing. So it's here. And then you had these two. And recall that k is I plus j. So you have this thing sitting here, and then lambda j ai. Now, this ratio of factorials is exactly d minus I choose j. So you get this expression. And then just, to omit one of them, just to omit I, because we are given k, we want to figure out what ck is. So j determines I. So let's just go from j equals 0 to k, that's the all values that you can take, and just replace I by k minus j. So it appears both here, and that's what you get. So that's ck. Now, it's really hard to actually continue from here, but it's easier if you know what to expect to open up your guess and see that you get the same thing. So on the other side, hand, let's look at p of x minus lambda. Okay. So I kind of forgetting about the previous calculation for the moment. So p of x minus lambda, in our weird notation, looks like that. I just put x minus lambda here instead of x. And then again, I'll use the binomial theorem. And now it's kind of start to get boring. So I use the binomial theorem, simplify a little bit, and I get this expression. And then if that's the expression, then that's the CL. It usually denoted CK, but here I switch from K to L in the middle. That's the CL, and you can look at it for a second and see it's exactly the same thing that we got in the previous sheet. Okay, so this is just, it's actually good to do it for yourself. It's maybe less insightful seeing someone else doing it or skipping some of the parts of it. But what I'm saying here is like the additive free convolution of a polynomial of x minus lambda to the d, then you, at the end of the day, get p of x minus lambda, which is expected. And it's expected because, for example, it's expected in terms of measures, but also it is expected if you believe that this is a generalization of the original definition. Indeed, here you can take A to be any matrix, any normal matrix. So you have this eigenvector basis, and then you put on them the eigenvalues that you want, which are the roots of P. So take any normal matrix A whose eigenvalues are the roots of P. So the characteristic polynomial is P of X. And let's take B to be x minus lambda, let's take B to be lambda I. So that the characteristic polynomial would be x minus lambda to the d. I mean, that's choice. You could have chosen other orthonormal matrices, but I chose I just for simplicity. And in this case, right, this Q and Q transpose will meet the I in the middle and the lambda, but that will slide through, and they will get canceled, and you will be left with A plus lambda I. And well, what's the characteristic polynomial? It's the determinant of xi minus the matrix. And from here, you can easily see that that's exactly P of x minus lambda. Okay. Good. So these are just a couple of examples to kind of, I don't know, start appreciating what's going on here. I think what you can appreciate is that it's not so easy to work with this explicit, be careful what you wish for. We wanted explicit formula, but it's not something that's so easy to work with. So the following lemma is kind of explains all these factorials, right? You see the factorials, you kind of have the feeling that someone used derivatives for multiple derivatives, and that's indeed true. And that's actually an easier way to work with this formula. That's the semi-explicit formula I was talking about. So the following lemma tells us that the additive free convolution of two polynomials can be obtained as follows. So there is this normalization factor. But then what you do is you go over all k from 0 to d, and you take the kth derivative of p of x, and you multiply by the d minus kth derivative of q evaluated at 0. Okay, that doesn't look symmetric, but you can also show it's the same thing as, I mean, it has to be, because it is symmetric, as taking the kth derivative of q, leaving it alive, times the d minus k derivative of p and evaluating it at 0. Same thing. Okay, so the proof of that is also not very illuminating, but let's just go through it for a second. So we are going to use the same notation from before. So this is P and this is Q. And then the kth derivative of P of X, I'm just going to prove this one, okay? The other one is the same. Or you can use the fact that you know it's symmetric. So the kth derivative of P of X is, well, okay, so we look at P of X, we derive each summand by itself, and k times, so you get this expression, right? When you derive once, you get the ith term, you get d minus I, and then d minus I minus 1, and so forth, and the exponent decreases every time by 1. So instead of writing these falling factorials, I wrote the entire factorial and divided by the tail that I'm not actually multiplying by. And this should be understood as it's always like implicit, understood as if I went too far, if I plus k is larger than d, then this is 0, okay? Okay, so this is the derivative of p of x. The elf derivative of q of x is the same, just with b's and j's and l's instead of i's and b's and k's. And I chose L just because I need to do, it's psychological, I need to replace L by D minus K. And then, so that's what appears here, it's just a calculation. And then we should evaluate at 0, at least this one. The P stays alive, but when you want to evaluate this as 0, the only J that survives is J equals K. And when the things that survives is d minus k factorial, because j equals k here, this is just 1 times minus 1 to the k bk. Okay, so you have this thing, maybe it's written in the next page, and you have that thing. Yes, it's written here. So with these two, if I'm going to open up what I claim is the additive free convolution, just plug in these two here and here, you get this expression and just some index theory, and you get the additive free convolution. I think it's better if you just look at the notes instead of looking at me going through the indices. But this is just to say that we have this other way of defining the additive free convolution. And with that, the main theorem that we are going to prove is what I said, is that this new definition of the additive free convolution actually generalizes our old one. So if you take any A and B complex normal matrices, I mean, it's as general as it can be complex, and it requires to be normal because otherwise you don't have this eigenvector structure. So, that is symmetric enough so that if you do har, it looks the same from every direction. If it's not like that, then the eigenvector structure has some more information that the har doesn't erase. So this is the most general thing that you can hope for, at least naively. So if you have these two such matrices, then this then the new definition of the additive convolution applied to their characteristic polynomials, P and Q are the corresponding characteristic polynomials, is the same as what we actually define to be the diff-Array convolution, namely the expected characteristic polynomial here with respect to har unitary, because everything is complex values. But you can replace it with har orthogonal if you assume that A and B are just symmetric matrices. Okay. So actually what's going to happen is we are going to prove it for a more general class of distribution, not just for har. So we are going to prove that this equality holds for many distributions, not many, but several distributions. And we just require a property that a distribution satisfying that property would have this equality. Okay. Okay, so I think I'll stop this here, and in the next video we're going to talk about this property, which is called minor orthogonality, and continue from there.